Today is a very special episode for two reasons. A couple of episodes back, we talked to Dr. Jowhary about quantum computing. Today, we have Professor Debdeep Jena from Cornell University with us. He is one of the world's experts in semiconductor physics. He's been building devices at the cutting edge of science and technology, particularly on the gallium arsenide side. And he's started several companies. He's led research at multiple universities. And for last decade or so, he's been also working at the cutting edge of quantum physics and quantum computing. He's also working on superconductors. But more than that, this episode is super special because Deep is also a really close one of my dearest friends. What I've asked Devdeep to help us understand is go all the way from early 1900s black body radiation and what anomalies scientists were discovering that led to realization of quantum physics to what's happening today with construction of qubits and larger quantum computers and what are the difficulties in getting there and what's the promise of the future. So let's get started. All right. Today is a very special episode for two reasons. A couple of episodes back, we talked to Dr. Jowhary about quantum computing, and most of what she talked about went over my head. And such is the nature with quantum physics and quantum computing, I guess. So today we have Professor Debdeep Jena from Cornell University with us. He is one of the world's experts in semiconductor physics. Um, he's been building devices at the cutting edge of science and technology, particularly on the gallium arsenide side and gallium nitride side. And he's started several companies. He's led research at multiple universities. And for last decade or so, he's been also working at the cutting edge of quantum physics and quantum computing. He's also working on superconductors. Um, but more than that, this episode is super special because Deep is also a really close one of my dearest friends. And I wouldn't have graduated from college if it wasn't for his class notes. He is also one of the most passionate and fun people I know who, when he goes into any topic, he goes really deep, whether it's playing cricket or quantum physics or anything else. So with that, um, I'm really excited to have this conversation with Deep and try to understand a little bit deeper around quantum physics and quantum computers. Um, what I've asked Deep to help us understand is go all the way from early 1900s black body radiation and what anomalies scientists were discovering that led to realization of quantum physics to what's happening today with construction of qubits and larger quantum computers and what are the difficulties in getting there and what's the promise of the future. Uh, so let's get started. David, it's so good to have you, or as we call him, Jenna. It's so good to have you on the podcast. I've been planning this for a long time.
Thank you, Amit. I mean, this is really also both a scientifically exciting opportunity for me to talk to you about some of the work we are doing and the community is doing, but also at a personal level. I think we always try to find time to talk about in a deeper way what we are doing, but we generally don't get a chance because we have to eat some good food. We have to hang out with friends and all that, which is I think we have enjoyed that a lot. But this is a great opportunity. I'm so excited. Also, as Amit, you said, I got this shirt. If you notice, this is our undergraduate institution, Kanpur logo. This was, I think, where we met for the first time. And I wouldn't have made it through abstract courses such as linear algebra and all without, your help. So, and I think we don't realize how much we help each other when we work with each other. And of course, we, in the same way, in both in research and in general, all our work. But I'm very happy to meet again in this format. Maybe this is the first time we're meeting in a more sort of official format to talk about work and science, which is great, and I'm very excited. Yeah, thank you, AP, for Amit. I also call you AP sometimes with your initials, so I might slip into that, once in a while. But very excited. So yes, this hour should be really fun. So,
All right, so take us back to the beginning of 19th century. What was happening in physics research, and what was confusing the scientists, and how that led to the nail spore models and EPR and everything.
yeah. So as you very correctly said, there's definitely a lot of things that one can talk about, but we can start by focusing on a very few key things that was a result of nearly, couple of centuries of laborious experimental work, where people were able to, experimentalists had been able to develop very precise spectrometers, and a spectrometer being the instrument where you can point it at a source of light, and it will count the intensity of light at different wavelengths that come and hit the spectrometer. And when they point it to various objects, they would see there'd be some wavelengths, a lot of light coming from those wavelengths and not from some others. But then when people started noticing very interestingly that if you point it at that time, as you might imagine, maybe 1800s and so 1700s, 1800s, steel industry was becoming very important. And there was a lot of metal being produced, steam engines being produced. So the efficiency of ovens, where one would melt steel, which I think we remember from our undergrad courses as well, martensitic transition, this, that. But anyway, these ovens, where they would heat up the iron ore to extremely high temperatures and melt things. So that there was all the companies and government institutions that were trying to do that had a big problem that this was a very inefficient process. So they would try to find all ways to pack in the heat inside and not let it escape.
Mm.
And how do you measure it? And people figured out that if you put a spectrometer and aim it at some regions and look around, you'll find where the heat is escaping.
Mm.
And quite amazingly, what people found is if you point the spectrometer, it will also, and you measure the shape. That shape had a very characteristic fingerprint of the temperature of that oven. And that radiation pattern is called the black body radiation. Basically, it's called black body because you don't want anything to escape. It's supposed to be a black body. It's not going to let anything escape, but something does. And that spectrum is, there's only one thing that determines the shape of the spectrum, and that's the temperature. Where's the peak, what's the shape, etc. And it's quite amazing. People could even point it at the sun and find the sun's surface of the temperature, or to stars and all that. And that happened before all that stuff. So that was one story that was mysterious because when people try to explain, already late 1800s, Maxwell came along, and before in Faraday and all, and they had understood that light is an electromagnetic wave, which is an oscillation of electric and magnetic fields. And the reason this also came from very laborious experiments by Faraday, who discovered the Faraday's law that you can actually, by moving magnets, you can create electricity and things like that. But the real sort of big change came when Maxwell. Faraday always had a hunch that electromagnetic wave is a mix of a little bit of electric and magnetic fields, but he couldn't prove it. He was a absolute, maybe the greatest experimentalist that ever lived, but he couldn't mathematically prove that light is composed of electric and magnetic fields. That came Maxwell, who looked up to Faraday and always used his experiments because he knew how accurately they were done. So anyway, Maxwell put together a lot of things before him, Biot-Savart law, Faraday, Ørsted's observations, Gauss law. And then when he was playing with the equations, he realized that there was a missing component that everybody before him had missed. And then when he introduced this displacement current term, which called, he realized that the light can propagate through space for billions of miles without dissipating, because the moment it creates electric field, and then if the electric field vanishes, it creates a magnetic field. When the magnetic field vanishes, it creates electric field, and they can self-sustain for eternity till they hit something or get absorbed, something like that. So, so that Maxwell's equations already showed what light is, right? But the black body radiation is kind of a curious mix of two things. One is light, the other is heat. And heat, in Maxwell's equation, there is no temperature. That's a whole new separate area of physics, right? Which is thermodynamics and heat and all that. And Max Planck was actually an expert, not in electromagnetic light and all that, but in heat, in thermodynamics. That was his area of expertise. In fact, the German government had given him multiple grants to go and look and work with the steel companies to find and solve this heat problem. And so he was always thinking of ovens and black body radiation all the time. And one of the biggest missing sort of mysteries at that time was when thermodynamic laws such as equipartition of energy, so basic fundamental founding principles of thermodynamics, that if you have, say 3 degrees of freedom, if a particle can move in 3 dimensions, then every degree of freedom when things reach thermodynamic equilibrium gets the same amount of energy, of half kT. That's the thermodynamic relation. So, when Planck, and before him also Rayleigh, Lord Rayleigh, Kelvin, Jeans, and they all applied thermodynamics to explain the radiation spectra, they would get that indeed at very small energies of light or very long wavelengths, it could fit to the point. It was very precise. But when the wavelengths got shorter and shorter, it would deviate. The thermodynamic relation would deviate dramatically it would predict way higher intensity at shorter wavelengths of light. So this was famously called the ultraviolet catastrophe, because ultraviolet is short wavelength and large energy. And the catastrophe here being, the theory fails spectacularly when you apply classical thermodynamics to the black body spectrum. And so Max Planck, who was trained as a classical thermodynamist, basically by invoking some very deep concepts which are related to entropy and disorder of a system, he realized that if in any degree of freedom of light, the energy that is allowed is continuous, just like a particle accelerating mass times velocity is its momentum, and square of the momentum by twice mass is the kinetic energy. So if any velocity is allowed, then any kinetic energy is allowed. So these are continuous variables. He realized that if the amount of energy in any mode of light can be anything, then the entropy would diverge, it would blow up. And it cannot explain what is physically true, that entropy is finite, it's never infinite. Then he realized that the energy cannot be continuous in any mode of light. And he, against all his classical notions, you can read about the struggle he had when he introduced the idea that the amount of light in any amount of energy in any mode of light is an integer times a quanta. So if the frequency of light is omega, h bar omega famously is Planck's constant h bar times omega is the energy, but that's not the energy. Energy is an integer times h bar omega. It can be 0 or 1 h bar or 2 h bar. The moment he introduced that and used the classical thermodynamics laws, not quantum, just classical, he could outpop the black body radiation formula, which was 1900 roughly. And every experiment that has ever been done since then has borne that this is absolutely correct, because the only sort of constants in that formula are Planck's constant, speed of light, and temperature. So it combines quantum, basically mechanics of light, electromagnetism, and thermodynamics in an amazing way. And its reach is kind of amazing. Sorry, go ahead.
I think that's where the term quantum comes from in quantum physics, right?
That's the birth of the word quantum. Absolutely, yeah. And what to me is absolutely fascinating about it is you can nearly almost all things you hear today about, say, cosmic, the features, cosmic feature that universes or galaxies are going apart, far, far from each other. All of them are measured using black body radiation. You can measure the temperature of a star, the speed at which it is retreating, speed at which it's going away. So that, and when we in our laboratories want to measure the temperature of something which is in vacuum, we can't build any wires to it. We can just look at the radiation coming from it, and sure enough, you can get it's 500 C or 800 C or something like that. So its reach is kind of quite dramatic, and it has always, so any black body radiation situation has. So that's the birth of quantum mechanics around the year 1900. And okay, so I'll stop here. If you have questions, then we can make the next step, which was quite interestingly from a person who made as much contribution to quantum as he opposed it. So anyway, yeah. So those are your best friends who always tell you, this sucks, but they always support you because they give you the greatest ideas. You have to do better, right? So,
yeah. Looking over me, right behind me.
Absolutely, right there. He's right there behind you. He's looking all over us. Yeah.
All right, yeah. Let's jump to the next one.
Okay, so that was all. That took people a lot of convincing, because most people didn't accept that. Oh yeah, somehow you have managed to fit something, but it doesn't do anything for anything else. It doesn't explain many other things. But what's kind of quite interesting is there were a couple of other experimental observations. One was the black body that we just discussed. The second was
It's
that if you
kind of
take,
like it's kind of like what we do in machine learning today. Just try to fit the parameters in the math equation to fit the reality.
Yeah, you're fitting constants, right? You're like, I have a model, and if I can if my model fits the experiment, or rather fits the data, then that's the science. And I think there was a very famous statement that if you observe a horse is running at, say, 1/5 the speed of light, but the horse is not light. The horse is a horse. It doesn't become your model of light. So I think we have to be a little careful about that. It's right. So right. So the other. So I'm going to. I love theory. I love the mathematical developments. But actually, in my opinion, most of these developments had hundreds of years of experimental evidence, incontrovertible evidence that were behind them, which I feel in general, most people who have not necessarily a direct, who don't work in this area, but do have an interest, don't get exposed to that part of it, which sort of is important, that these things didn't come out of nowhere. And Planck and Einstein used decades and centuries of experimental evidence to synthesize and bring a new understanding, right? So anyway, so the other one is in similar vein, was already when optical spectroscopists were measuring a spectra of pure elements, and a great example being hydrogen. To measure the spectrum point, create very pure hydrogen gas, which people could around late 1800s, and then shine some broadband light on it and look what is coming out. They would see not black body spectra at all, completely different thing. They would see extremely sharp lines of spectra, light coming at a particular energy and nothing for a while, and then another particular energy and nothing for a while. So these were called atomic spectra. And and obviously the premium one being the first element in the periodic table, the creation of the universe started, I guess, there and all that. So and the universe is 99 point some percent hydrogen. It takes a lot more effort to create the next atom and then the next, right? So you have all the machines in supernovas that create the heavy atoms, but the first was supposedly after Big Bang was hydrogen, right? So. And at least the surface of the sun is primarily hydrogen and helium and all that, right? So nevertheless, okay. So when they measured that, then it had these very sharp lines, and many people measured this with great accuracy. Rydberg and Balmer and all that. I mean, they discovered these different lines, and that even Planck had no explanation for. So absolutely no explanation, and that took some while to figure out. But so one of the people who was always quite interested in this angle and believed in Planck very immediately was obviously Albert Einstein. And at that time, he was thinking not so much about atoms and all that, about spectra, but he was thinking about relativity, as you know, and that why he was thinking about another discoveries of Maxwell, that is speed of light, right? And the people started measuring and subjecting light to notions of classical physics, that if I am moving at 30 miles an hour in my car and you are coming towards me at 20 miles an hour, then my relative velocity compared to you is 30 plus 20, which is 50 miles an hour. I think we all have had experience of sitting in a train and moving, and then not knowing whether I'm moving or the other train is moving, right? When you're at a station, or if you're moving at the same speed, you can't even say whether you're moving. So that's the principle of relativity, which is not, that was realized well before Einstein by Galileo and others, that velocities are relative. But Newton, Galileo, all of them made very specific statements that velocities are relative, but time is not relative. Time is the same for all observers. And I know this is going in a slightly different direction, but it is very much connected to this bigger story. Right. So the Einstein saw some experiments that were done by various groups around the world, including in the US by Michelson and Morley and all, where what they were trying to do was seeing that if the Earth is rotating this way and a light beam is coming this way, the radial velocity of Earth and the velocity of light, will they add when we're rotating this way, and will they subtract when I'm going away, right? So this is the famous Michelson-Morley experiment, where they said that I should be able to measure the relative velocity of light. That was the main idea. And when they measured it, it was always C. It was always 3 times 10⁸ meters per second, no matter how fast the observer was moving. And that was very mysterious for many, many people. And Einstein said, I'll tell you why that is, because nobody has realized why that is. And then he literally took this carpet, pulled the carpet from under our feet, that time is absolute. He just said, no, time is not absolute. Time behaves very similar to what velocities do. That time is also relative, depends on the observer. And we don't go into all the details, but with this minor, also dramatically major change, he showed that velocities add or subtract, but with an additional factor, which is called this Lorentz factor, which has the speed of velocity over c, speed of light squared, and their time will dilate or expand based on how fast a person is moving. Somehow nature always finds a way to maintain this sort of cosmic constancy of the speed of light. I mean, it cannot change. Everything has to bend around it, so to speak. So that was his first theory of relativity, and then he outpopped from there by enforcing Newton's laws, like momentum, energy, that energy must be mc squared. All that stuff came out from this this is special theory of relativity, where he introduces that light has the constant speed, and then everything has to bend around it in velocity. So he was thinking very deeply about light already. And when Planck's concept came along that light is not what people have thought about, but it is only carried in energy in light, is only carried in quanta, that really piqued his interest immediately. And he made a very deep connection that when light interacts with matter, when a light beam hits a metal, for example, the other experiment, which Einstein had clear evidence for and people had measured, is called the photoelectric effect, that you can shine as much light as you want, but if the energies or the wavelength is above a certain cutoff into a metal, it will not be able to eject any electrons from the metal, no matter how intense it is, so to speak. But if you go above a certain frequency or below a certain wavelength, now every light particle you don't even need much intensity. You'll get electrons ejected out. And this was famously explained by Einstein by using Planck's idea that light energy comes in packets. It's not a continuous beam, it's not a continuous stream. And the moment you introduce this, you get that one electron or a particle in an object can only swallow, so to speak, one photon at a time. It cannot swallow 100 photons or 100 the energy, but it can only do one. And it has a certain energy that it needs to escape. It's in some swimming pool. It needs a certain height of the swimming pool to get out of the pool. And it can only happen if you give it that quanta or more. It can't get out if you have hundreds of less ones. It cannot do steps.
And
so that's
the energy in a quanta is directly proportional to the frequency.
That is correct. And the constant of that proportionality is the famous Planck's constant. So energy is Planck's constant times the frequency. E is h nu or h bar omega, which that's precisely it. And the energy, the actual energy is an integer times that. So this is the discrete box you can fit it in. So the actual energy will be an integer times that in that particular frequency mode, right? And so that was Einstein's explanation for this other experimental fact, which really is very practical, because photoelectric effect is used today in so many things, ranging from photodetectors to every solar cell. A photovoltaic cell is when the light hits and the electron is released. When you collect it and create a voltage out of it, you convert light into battery. That's solar cells. So that underlies all communication systems. If you have data going through an optical fiber, the other end of the fiber, you have a photodetector that's counting the zeros and ones as light pulses. So this is sort of underlies so many things. This is just a few from our point of view. These are where we use it. But what's quite interesting is Einstein also tried very hard to explain the spectra of hydrogen, and he couldn't. He tried very hard and he couldn't, and not because Einstein was not smart. Nobody should ever say that, because he was obviously on top of things, and people have always been as clever as they can be. But what was missing was experimental evidence of that was a crucial one that was missing about matter. So that came around 1911, 1912, about a decade after Planck's theory. This came from Rutherford. This is the famous experiment where he was shooting these sort of alpha particles into gold. I mean, so basically the crux of the matter is he discovered that the mass of the atom is really concentrated in a very tiny point, nearly, about, I don't want, maybe million is too much, but about 10 power minus 5 times the size of the atom. The mass of it is in that little point speck in the middle, and that's the nucleus of the atom. So he discovered that the mass, so electrons had already been discovered, around 1890, around 1900 by J.J. Thomson and others. So they already knew that there's a particle of mass 9.20 minus 31 kilograms and charge exactly equal to that. That was the elementary charge that was discovered in 1900. But people mostly thought that, yes, there's a negative sort of jelly and the negative charge, which is very light, that's floating around like a gas. But then the positive jelly of material, that's where the actual mass of, say, a piece of wood or copper comes from. But what Rutherford discovered was, no, not quite true. All the positive charge is concentrated in this little tiny, nucleus, just like a living cell, if you think of it as a nucleus and then the cell body around it. This is even more dramatic because I think the example people give is if you are in something like a football stadium, then the nucleus is the size of a pea, or an M&M, for kids perhaps, compared to the same. So it's very tiny, whereas the electrons are sort of wandering around the entire stadium. But this is it. And in his lab, so when they discovered it, in his lab was a visiting postdoc student or a postdoctoral scholar, and that was Niels Bohr. He was visiting from Copenhagen. And Niels Bohr was a very interesting character. I mean, if people have chance, they should read about him because he's clearly a Westerner. I mean, he grew up in Copenhagen, in Denmark, but he was a very much of an Eastern philosopher. He always had this notion that everything is connected and it's not like black and nothing is black and white. That's anyway. So that's a little bit of a his personal part of it, but he had been very well aware of all the spectral lines that had been measured by the Swedish physicist Rydberg and others. And he knew in the back of his mind, and many other people knew, that this is an unsolved problem. And there must be an explanation for it, right? Why hydrogen has these very sharp spectral lines, whereas a black body radiation is all broad. And then when in Rutherford's lab, when he was visiting there, he saw that data and he realized that this is very interesting because let me apply classical physics of classical mechanics. What does classical mechanics mean? Basically, it's Newton's laws. So you have an electron that is negatively charged, and look at a hydrogen atom. You have a proton that's positively charged. And now an electron is wandering in some orbit, perhaps size of a stadium compared to a nucleus, or in a microscopic scale. And how can I find the energies of this system? The energy of an electron is basically its kinetic energy plus its potential energy, according to classical physics. Kinetic energy is half times mass of electron, which was known precisely at that time, times the square of its velocity. And the potential energy, these are two charges, positive and negative, equal and opposite. If the distance is known, it's the Coulomb, u squared by 4 pi epsilon r. So add those two up, and you realize that, well, the energy is continuous. Well, kinetic can be anything. Potential can be anything. It can be any distance. It can move at any speed. And then when an atom is making a transition between two states, when you hit it with light, it's not emitting a continuous stream of energy. It's only emitting very sharp lines. So something has to give. It's not correct. Something is wrong here. And that was the first realization, because I think we all know that the first, we start with denial, but we have to accept something first, that something is wrong. And so he was the first to realize. He already realized that, by the way. I mean, that was not, but then the fact that the proton is in the nucleus and it's a point concentrated charge, that was not known to anybody before this discovery, neither to Einstein nor to Planck. And so he tried a couple of things, mathematically, and he found that quite amazingly, he was thinking at the same time about, cosmic phenomena, about planetary motions. I mean, everybody was. Physicists at that time were not only thinking about one thing, but generally quite broad. And he started building, saying that what if it was going in an orbit, like we just talked around, just like the planetary orbits, the Earth going around the sun. Obviously, the Earth doesn't get attracted to the sun too much, luckily, so meaning well, it has a gravitational force that attracts it. It's very weak, but then the centrifugal force keeps it apart. But here, it's a dramatically different situation. Here, you have an extremely high force that's attracting, and these are Earth and Sun are not charged bodies, but the moment you have charge and it's accelerating, it radiates energy. So as it loses energy, the electron should gradually, the energy is the velocity of the electron would keep it far from the nucleus, but as it loses, the velocity would decrease and it would spiral in, and it should, crash into so the proton should capture the electron sooner or later because it's losing its energy, which happens when you have asteroids that don't have enough energy and then they get, hit the Earth,
Crash
so
into
to
the
speak,
sun.
and or cause elimination of dinosaur species, for example, even into the Earth, right? So in the same way, it says it should happen, but obviously it doesn't happen. In fact, not only is not that doesn't happen, elements are some of the most stable things in the universe. I mean, if you create a hydrogen atom, it's very hard to get rid of it. So you can't really just sort of do that, and so there's something dramatically wrong here, right? So that was Bohr's thing, and he kind of came up by doing some, I talked about Einstein had this sort of Planck had this thermodynamic intuition, and Bohr had a very classical intuition that the difference of energies has to be discrete, and if it is continuous, or if classical physics works, then atoms should be unstable. We know it's stable, though. It is very, very stable. So there's something quite wrong here. And so he introduced, by playing around with this idea, that he saw that if he introduces that the momentum of which is the mass and the velocity of the electron, is not continuous anymore, but it is quantized, just like Einstein did. And big surprise, the quantization involved Planck's constant again. So he saw that if he takes the momentum and he multiplies it by the circumference, momentum times circumference, that's typically called this total angular momentum, let's say. So momentum times circumference is an integer times Planck's constant. And then he found that then you square the momentum, divide by the mass and all that, you get the kinetic energy. Now that's quantized. You add kinetic plus. So it also says that the orbit should also be this orbit or that orbit or that orbit, nothing in between anymore once it's quantized. So it locks all these in. And then when he did the energies and took the difference, and lo and behold, it got exactly the Rydberg's spectral lines. So this was the discovery by Bohr, so-called the Bohr's Bohr orbit theory, sort of as a throwback to the planetary orbits that were explained by many physicists before. But this is the electron orbiting around the nucleus. And it gave discrete energies, and not only discrete energies, the energies that were absolutely precise and explained the spectral lines that had been measured for about 100 years or so before him, and nobody had any explanation for. Now, what it did was it had, in addition to all the other quantities, it also had the mass of the electron, and basically it was a true mechanics. It's not light anymore. It's real mechanics, light matter. So essentially, this is the birth of quantum mechanics, meaning mechanical laws like Newton's laws. How would it be modified? And that was Bohr's model. So yeah, so that was a big revelation. That 1913 or so, about maybe 10 to 12 years after Planck, and nobody even remotely understood why this must be so. Why? So even Bohr didn't give an explanation about why will the momentum be quantized. That came again 1 decade later. But if you take that at face value, just like you said, you build your model and you say, here are my coefficients, right? It explained a great mystery, right? So then that there was some truth to it, obviously, and that was the they all, Rutherford and all these things also gave birth later to nuclear physics and all that, but that's a separate thing, separate direction. where you try to, break the nucleus apart. But as far as basic quantum goes, I think this was the birth of quantum mechanics itself, where we kind of realized that at elementary scale, momenta and energy, all these things that we thought should be continuous are also quantized. So, yeah. So anyway, I can maybe pause here a little bit, and if you have questions, or
It was
any
so fascinating.
corrections.
I feel like this is the first time I am actually understanding quantum physics.
Well, we all understood it when we took it for the first time in a course, and then we forget it, right? So,
Yeah.
and only those for whom it becomes a job, also a joy for me. I mean, we
Mm,
kind of keep doing it all the time, and
mm,
oh, yeah. So, but I think this is very, very interesting that it has these trails, which sometimes maybe are explained, but when you
mm.
are essentially solving math problems, you don't realize there are all these people involved, so that's quite interesting, I feel. Yeah.
Yeah, and I think what's most interesting to me is like when you read it in abstract, it feels like somebody just out of vacuum came up with this theory. But
Mm.
there is a struggle behind each kind of this revolutionary idea being put forward that like here's what we're seeing in experiment and we just cannot explain it any other way. And that's why this must be true. And probably took a lot of courage for each of them to kind of break from the conventional wisdom and put something like that forward.
I mean, that people were prosecuted for that, the some famous people being Galileo
Mm,
who said that no, Earth is not in the center of the universe, and that went against the teachings.
mm,
So I think the world has changed a little bit, but scientific community is still, we get tied to ideas that
mm,
that we believe are true, but when in the presence of experimental evidence, it I think all of them were sitting on the shoulders of the previous experimentalists, so to speak.
mm,
And I think when Nietzsche shows something experimentally,
mm,
we all of us should and we do pay a huge amount of attention, because that means that there's a mystery there which all our predictive theories have not yet identified, and so the theory is
mm.
incomplete. One has to revise it,
Yeah.
and one has to accept it sooner or later, because that's the truth. That's a bigger truth. The
Mm,
older theory was still a truth,
mm.
but not the whole truth. Now we have to go to a bigger truth, and that's always hard to digest initially, but we all come to terms with it. So yeah,
So
right,
let's come back to Einstein and the whole EPR thing, because that's
right,
what
right.
makes quantum computing possible, right? Yeah.
Absolutely, yeah. So maybe what I'll do is the EPR came in the next step after Bohr, because
Mm,
what Bohr model explained was the spectral lines of hydrogen.
mm,
But what's quite amazing is that the moment you apply it to the next element, which is helium, it doesn't
mm,
work.
mm.
And that's crazy, and the reason for that is there is more than one electron. There are two
Yeah.
electrons there, and
Yeah.
this is very fascinating. It doesn't work for helium or for any other element of the periodic table.
Mm,
Only for
mm,
single electron theory it worked,
mm,
and there was no sort of deeper. One couldn't sort of derive why it should be quantized. It didn't come out from the math, so people
mm,
knew that there was something else here.
mm,
Uh, and that came a little bit later, about 10 years after that,
mm.
where we're getting to how the EPR actually would come to being. So then,
I guess before that we have to
uh,
talk about Schrödinger, right?
that's right. So that's where to
Mm,
get to now. Yeah.
mm,
So that's right. Yeah. So then, mm, around 1924-25 is when there were two things that happened quite interestingly. One of them is light was Einstein, again, coming back to him,
mm,
around 1917. He had a very remarkable paper. He wrote a
mm,
remarkable paper where he was trying to sort of, Planck uh, introduced the idea that light is quantized, and this quanta are called photons, individual
mm,
quanta are called photons. But in Planck's model, the nature of what is the matter, the black body itself, was sort of, it was not really discussed at all. It came by focusing completely on light itself. But actually, Einstein knew very well that the black body radiation is not a property unique to light. No, it is also a property of the matter with which it is tied up, where it is coming from. So he wrote a very interesting paper which introduced for the first time this concept that again had been missed before him by all spectroscopists too. This is called stimulated emission. Stimulated emission from light. So essentially, when an atom looks at a photon that's coming, it can absorb it, no problem. That's called the absorption process. And absorption always needs a light particle to be present for it to occur, because there's nothing to absorb. And emission was always thought that, well, if you think of a hydrogen atom and go back to Bohr model, you have two levels, second level, first level. And if an electron is sitting at the higher energy level, it can relax to the low energy level, and it can emit a quanta of light, one photon. By the way, this is used in quantum computers today, where single atoms and you create the photon. We'll come to that hopefully. Yeah. So, and these were the two processes known: the absorption and emission. But when Einstein used these two processes as the fundamental process of light-matter interaction and brought in photons, like Planck with single quanta, he saw that he couldn't derive from here by introducing the fact that the atoms have to sit in some thermodynamic equilibrium at a temperature T. He could not derive the blackbody radiation from if the only two processes were these two. Then he realized there's something missing. And that missing component he realized was the following. If an atom is sitting in an excited state, electron is sitting in the high level, and a photon comes along, which is exactly the same energy as the difference between the higher and lower energy. Then when the photon goes through, the electron will drop to the low energy and you will get two photons. Right? There was one we started with, and then you have two. But this second photon has a very remarkable property. The second photon is a complete clone of the first photon. Its energy is obviously the same because it was matched, but its phase, its angle, the direction in which it goes is all the same, exact copy of it. And this process is called stimulated emission. There's a normal emission which is called spontaneous emission, where electrons is in high level, there's no photons, it drops and emits. Now that photon goes in any which way it wants. There's no restriction. But the moment you have one photon come in and then this happens, stimulated emission, it copies itself, it clones. And you can put a mirror, feed it back in, and if you have another atom in an excited state, it will copy itself. So suddenly it builds up, and that's the idea of the laser. It's a light amplification by stimulated emission of radiation. Anyway, so that was introduced by Einstein because he was trying very deeply to understand the nature of matter.
So when did we discover stimulated emission experimentally, and how did that turn into laser? Was it a long period or immediately?
It was a very long period, and it's kind of quite amazing why. That's sort of so the Einstein's paper came in 1917. And
this based off of somebody else's experiment, I guess?
No, this one was trying to explain. So here's Einstein's genius, where he predicts that this physical phenomena must exist of stimulated emission, because without it, you cannot explain Planck's blackbody radiation. It cannot explain it by combining thermodynamics and the actual nature of matter. That fact is matter has discrete energies, which was discovered by Bohr. You cannot explain Planck's blackbody radiation if you don't introduce stimulated emission. So this is necessary.
It's pure theory at this point.
It is completely theory. It was discovered from theoretical considerations, but with the two experimental facts. One is your blackbody radiation, and the second is your atomic levels at electron energies are discrete. So those are the theoretical inputs. From there, it concludes that to be consistent, you must have this new physical process that people have missed. And sure enough, people measured, and indeed there was stimulated emission. What was quite interesting is the first laser was actually made in the microwave, not in the visible wavelengths. And that was in 1960. sorry, 1952 or 53 by Charles Townes and all in Columbia
Mm-hmm.
University here. And then the first optical laser was made in Hughes Research Lab in 1960. You can imagine 40 years, 40.
Mm-hmm.
And there's an interesting notion behind it because most physicists understand physical processes very well, but things such as feedback, feedback loops and stability of systems, that was completely the forte of electrical engineers, and they generally were not really talking to each other much. But I think von Neumann and all sort of also instigated that one can actually build a laser. Laser sort of is a crazy device which seemingly would violate some uncertainty principle and all that. But anyway, that's a slightly different direction. So maybe we can
Yeah.
getting back to this idea that early 1920s, Einstein, right after the stimulated emission paper, he got a very interesting letter from a physicist very close to my hometown and your hometown too in India, from Calcutta, from a famous physicist called Bose. And Bose had a letter saying that so the stimulated emission and your earlier papers and the Planck's blackbody radiation points to a very interesting nature of light itself. That if you have in one mode, one photon, it increases the chances of having another one in that mode. This is nature of particles which are called bosons, Bose particles. So every particle that has ever been measured or found, elementary particle in the universe till today, is one of two kinds, and one of them is bosons. So, so this is called, Bose. So Einstein received that letter and he immediately published it because he saw that that's a great idea. Even Einstein had not realized that. And this property of bosons is that you can put as many particles as you want in one state. There's no restriction. In fact, the more you put it, the chances of having more, it increases thermodynamically the chance of having even more. So it wants to condense into one state, which is famous Bose-Einstein condensation of that kind of particles into one state.
So
So a
bosons
laser
comes
might
from
be
Jagdish Bose.
That's right. That's named after him. And I know we all feel proud about our connections to this, but yes, absolutely. Half particles of the universe are is named after Bose himself. Yeah. And so light, all kinds of waves, typically photons, phonons, sound waves, they can condense into one state. Laser can be thought of as a Bose-Einstein condensate of light particles because all of the photons are going in the same direction, same mode, same wave frequency, and all that sort of thing. So that happened, and at that time, there was the other famous physicist in France who was a Nobel himself. He was really a prince. He had no reason to do physics at all, but he did it as a hobby. This is Louis de Broglie, who in his PhD thesis, he kind of, from very interesting considerations, said that, why should wave nature be limited only to light? He kind of, I'm saying this in a very crude way. He said that all things in nature should have wave nature, in addition to light itself, sound itself, but also electrons. They should also have wave-like nature. And it comes from very interesting considerations, from relativistic considerations and all that. And it was a hypothesis. And what he kind of realized is this quantization condition that was introduced by Niels Bohr, where that the orbit, if you take the momentum and you multiply it with the circumference of the radius, circumference of the orbit, it must be an integer times Planck's constant. This is the famous Bohr quantization condition. And he realized his theorem, or the de Broglie theorem, is very interesting. It says that the wavelength of anything is equal to Planck's constant divided by the momentum of that thing. That is that famous de Broglie, or the momentum is equal to Planck's constant by the wavelength of it. Very simple relation, but very profound, because that means that no matter whether you have light has some momentum, or you have an electron, it has a wavelength now because it has a momentum. Obviously, its wavelength is, for a similar momentum, the light has way less momentum. It can. And we are all getting hit by millions and billions of photons right now, but we're not feeling it. But, if it was a cricket ball, you would feel it, right? So the mass does make a big difference here.
Yeah.
So anyway, so de Broglie introduces that relation without having any experimental evidence, but he knew from the Bohr model that there's some connection there. And that experiment was done around the same time in Bell Labs, not too far from here, near New York City. This is called the Davison-Germer experiment. What they were measuring in Bell Labs at that time, late 1920s, mid to late 1920s, is Bell Labs had the very practical goal of connecting the entire country through telephone networks. They were Graham Bell had founded the company because he had he had invented the telephone itself, and said, well, like if I can talk across streets in New York City or from New York to say Ithaca or Syracuse, why not from New York to San Francisco? Let's build one. We should be able to make phone calls with that. And for that, they needed amplifiers where the signal have to be sort of electrical current signal has to be amplified every now and then because there's loss in the copper wire it goes through. And that is a very practical concern. So at that time, the real amplifier people were using were called these vacuum tubes. Essentially, you have a glass bowl and you have a metal, and you evacuate all the air out, and you have a metal piece, and then another electrode here, and you literally flow current through the vacuum. Electrons go through the vacuum. This is called a cathode ray tube also. If you remember our old TVs, we all had that screen, right? So the vacuum tube is a much smaller version of it. And by using a 3-terminal version of it, sort of 3 electrodes, a collector, emitter, and a base or a grid, you can amplify an electric signal quite efficiently. So there were this whole division of Bell Labs where they were trying to make better and better amplifiers, more energy efficient, higher frequency, higher speed, sort of thing. So there was once a very interesting accident in their laboratory where they were doing this experiment with nickel as the metal. Electrons were incident on the nickel, and then they would bounce off, and they would collect it and they could see the electron patterns. So they had an accident where the glass cracked, and then the air leaked in, and the nickel, whenever anything is exposed to air, it oxidizes. So it formed an oxide layer. And the electron reflection was very weak. So that what they did was they sort of internally heated up the nickel a lot, and they closed the vacuum, and then electron beam hits, and then they looked at the detectors, and the beam of electrons hitting a solid and reflecting, and what they observe is not what you'd observe when a beam of classical particles hit an object, but they saw it's as if it's diffracting. There was a wave-like pattern. There's as if light is passing through a
banks
slit,
of
but there's
intensity and lack of intensity.
That's right. And this is a beam of electrons, not. This would be quite natural if you have a sound wave going through two slits, and you observe and you see the bands, or you have a light wave going through Young's double-slit experiment. But this was nothing to do with that. This was electron beam, and they were quite surprised. They're like, "Hey, what's going on?" And then they start changing the energy of the electrons.
Why was there measurement around it to measure electron, or was it kind of?
Great question. So this is they would always try to look at the this metal is generally used as a grid to control the. So the measurement apparatus was really let me tell you what exactly it was. It was basically something that scintillates when an electron hits it. This was same as what's used in cathode ray tubes as well. So it's essentially like a phosphorus. If your electron hits it at a certain energy, it will give a pulse of green light. You can see it visually almost. But so the reason is they were. This is a metrology tool to make better vacuum tubes. Just you want to control the reflection and the transmission of electrons through a thin metal grid. So it's a metrology tool, and in that metrology tool, they used to. It's like you're measuring the signal for that purpose. So this didn't serve. It didn't serve a purpose in the vacuum tube as much as just to make it better by studying the reflectivity of electrons from the surface. Anyway, so they observe this, and quite interesting, they start tuning the energy, and then they see that as it change the energy, the separation between the bands would change. and they didn't have a theory. And actually, Clinton Davison was visiting a conference in Europe when he found from his colleagues there that, hey, de Broglie has this very interesting idea that the momentum of electrons should be equal to Planck's constant wise wavelength. And he immediately did the numbers and he's like, this is spot on. It's absolutely right. Right. So this was sort of very interesting. And he comes back and then they redo all the experiments carefully. And if you actually, Bell Labs has their sort of a historic site right now. If you go in, you'll see, the discovery of the wave nature of the electron. There's a plaque with the actual data of the first interference pattern of the electron. And here this grid is the fact that the nickel, when it crystallizes, it forms the uniform array of atoms. And the wavelength of distance between the atoms is precisely the wavelength of the electron that's incident, roughly of that order, then that diffracts and it forms these beautiful bands. So anyway, this was the discovery of the wave nature of the electron itself. And this was sort of the final straw, so to speak. The moment this was discovered, around that time, both Heisenberg and Schrödinger were trying to basically give a firm basis to Bohr's ideas of revision of Newton's laws. And there's a little bit of a twisted story behind there too, but I think for the most part, I would say that the fact that our electron must live this, Jekyll and Hyde, or two lives, both be a classical particle, a point particle, but at the same time it must have a wavelength. That immediately led to one has to revise. So, for example, if you have a wave, and a perfect wave is spread out over space, it must have a large number of wavelengths. But at the same time, how is it that you can have both the location of a point particle and the fact it's extended object? Mathematically, how do you capture that? Right? It's not Newton's law says, well, force is mass times acceleration, but in those, what's implicit is the mass is a point particle. It is at some point in space, it's moving at a certain velocity. So its momentum and location are precisely defined. Right? But if you have an electron now, it has a wave, so it's spread out. Right? Wave has to be spread. A point cannot be a wave, so to speak. But it also has a location because it can hit a screen. We know where it is at that time. So both actually, I would say, if you think of Schrödinger's formalism, he realized that the state of the particle cannot be represented by a set of two numbers, like its location and its velocity, which is true in classical physics. It has to be represented by a mathematical object that has both, but also has baked into it the de Broglie relation. It must be that the momentum and the location wavelength are tied in there. So he realized that it has to be a function. It cannot be a set of two numbers. And that's called the wave function now. So essentially, this must be a function. And what is the function mathematically? It is a solution to some differential equation or some matrix equation, perhaps. So that's and then Schrödinger tried, and he didn't have to go too far. What he did was the classical physics has the Hamiltonian formalism, which says kinetic plus potential energy. It has a Lagrangian and Hamiltonian formalism. So he kind of said that then he sort of modified that version, said that we have a wave function and this operator which acts on the wave function will give you the energy now. You give a differential equation. Before him, Heisenberg had discovered the matrix formalism of quantum mechanics, where he introduces the matrix version. Why? Because people knew very well that matrices have, so the solution of this is the energy of the particle. And many people knew very well that matrices have discrete energy eigenvalues. When you have a matrix, it can have discrete energy eigenvalues that's consistent with the spectra of hydrogen atom. So mathematical structure of it was, Heisenberg's version was matrix, whereas Schrödinger's version was a set of differential equations. These are called the Sturm-Liouville differential equation version, which allows for both continuous and discrete energies. Anyway, so this is the wave-particle duality of both waves and particles. We don't want to call them either now, of quantum objects, let's say. And with this, the moment you introduce two particles, not one, first of all, the Schrödinger equation explains perfectly the hydrogen spectrum, almost perfectly. Now, the moment you introduce two particles like helium, and you are forced to, we are forced to consider another very interesting phenomena that was missed by Bohr as well, which is the distinguishability of the particles. So this function we just mentioned, I don't know if I'm going in a direction that you would, is this a good direction, or we should maybe talk about the quantum part of this? Yeah, right. So
no, I mean, the goal is at the end of this to have some understanding of how qubits work.
Qubits, yes.
So,
and I think we are on track, though.
Yeah,
we are on track.
yeah.
So, so essentially, if you have two electrons, then the problem with the fact is these are elementary particles, which means that two electrons have all same mass, same charge. There's another aspect which is spin. They kind of same spin. Now they're indistinguishable in sort of fundamental way. In a very fundamental way, they're indistinguishable. And whenever you have indistinguishability, when you write a wave function for two particles, the square of the wave function gives you the probability of finding a particle here and a particle there. Then this indistinguishability forces another consideration on top of the nature of quantum particles itself. That if particles are indistinguishable, by the way, an electron and a proton, they are completely distinguishable. So this law I'm going to mention is not, though they are distinguishable particles are not subject to this law. But if they're indistinguishable, they must satisfy an additional mathematical criteria that if you swap the particles, particle electron is point A and point B. If you swap the two locations and no physical property can change, that's the meaning of indistinguishable, right? To swap two particles. And mathematically, that is captured by the fact that when you square the wave function, it should, x1 and x2 are switched. It enforces some considerations. And from there is born this fact that there are only two kinds of possibilities here. One is bosons, which we already talked about, that you can put as many particles as you can in one state. And the other one says only one. You can't put more than one. This is the famous exclusion principle, a Pauli exclusion principle. It's sort of mathematically proven from here that, and electrons are this kind of particle where you can't put more than one in one state. So this is these are called fermions after Enrico Fermi. So all particles in nature are either bosons, where you can put as many as you want in one, or they're fermions, which is you can only put one, no more than one. So all matter, the periodic table, the existence of the periodic table, all the elements can be explained from the fact that they are fermions. Electrons are fermions, so you can't put all the electrons of say 10 electron system in the first electron state. You have to go some in first, then second, so you get hydrogen to helium. The periodicity, all of them come from here. So now quantum. So that was sort of the formation of. Yeah, go ahead.
This may be a relevant question, but wasn't there that SPDF and you could put two electrons in the first orbit and 8 in the next one or something like that?
That's right. You're absolutely right. So when we put two electrons in the first orbit, they can only go in if they have opposite spins. So there's the additional degree of freedom with the angular momentum, in which case they're distinguishable again. So two electrons with different spins are distinguishable. They're like two bar magnets. One is pointing north, the other is south. So they're distinguishable. But this is the Schrodinger's principle that if you want to put two, they must have some distinguishing features, in which case they are still distinguishable. So right. But this is a quite solid rule that you can't violate for fermion-like particles, right? So this also gave a very interesting that is the birth of so much, chemistry, solid state physics, all of that sort of came out of the classical computers, came out of all these things, considerations. But it also gave birth to a very interesting notion that if you consider just one hydrogen atom, then you can create a very interesting situation in a hydrogen atom where you can have an electron in the ground state, but you put that atom inside maybe a box, and you have two mirrors, and you have a light or a photon, single photon that's incident on this atom with exactly energy matched to the ground state and the first excited state. So then let's say the light photon comes back and the atom absorbs it. Now it goes to the excited state and it sits there for a little bit. But then, it will sooner or later spontaneously emit. So it falls and it emits the photon back, right? So now, let's say I'm sitting outside this box. I want to know, well, is the hydrogen in the excited state or in the ground state? I'm not quite sure now, right? So, yeah. So this is called a very interesting case of superposition. You have a superposition of a state in the ground state and the excited state. And this is where the birth of quantum computing, this is the core idea of quantum computing, that this object is called a qubit. It has, if it's in the zero state, it's a classical bit, say call it 0, right? If the first excited state, let's call it 1. Then that's a perfectly well-behaved excited state of atom. That those two are classical bits.
Yeah.
All classical computation today is done with zeros and ones, and essentially instead of a hydrogen atom, what we're using is I put 100 electrons in some metal plate, and then I use a semiconductor, to detect it or write it there. If there are 100 electrons, well, that's a 1. If there's zero electrons, 0 or maybe 10 electrons there, that's a 0, right? And all data today, all memory, all computation is done using, a certain number of classical particles that you can transduce and measure and distinguish between it black and white or 0 and 1. So if you think of a sphere, so to speak, you are either in the North Pole or South Pole, let's say. So that's a picture one can have, a vector pointing there or there, and your entire Boolean logic, AND gates, NOT gates, you can flip. If you flip from North to South, you go 1 to 0, that's a NOT gate. A NOT gate is a reversible gate. You can, if you have a 1 coming in, 0 goes out, you can always recover what you did get from the beginning. But classical computation and Boolean logic, as you know very well, and most of us, you have this set of universal gates to do computation, right? NAND gate is a great example, where you do A and B, and then you take the NOT of it. And from the NAND gate, you can create the NOT gates and other gates. So it's a universal gate.
Yeah.
But what's kind of very painful, it does wonders already. I mean, we are all doing LLMs and all that today. So AI, it's all based on classical Boolean logic, right, of zeros and ones. But what's quite interesting is no matter how hard you try, you take a NAND gate, it's not reversible. Meaning you feed in 1 and 0 or 0, 1, and the output is either 0 or 1. So you can't recover what your inputs were. So you have lost that.
Yeah.
So in other words, the information is flowing unidirectionally from the input to the output. There is no way going back. This is very important also because it makes the system extremely robust. It sort of makes it immune to noise and all that. But you can't recover things, and it's quite wasteful. It costs erasure of information, costs energy. So, and that's why
this is probably an important point that most of us don't get. Why is erasure of information linked with energy loss?
Yeah. So now this is a very deep question too. At the same time, I should say, I would say
Are we jumping ahead? Should we go back to sort of
maybe we go back to EPR and come to that. I think so. Yeah, and entanglement. So let's get to that because and then we will come to this because
also
I think it's a very
talk a little
question.
bit about phase and like how that plays a role. Right?
Yeah. Right. So now so the classical scenario is that, and maybe just sort of to conclude that part of the story, that it's not like all classical gates for computation are irreversible. There are like C0 gates and all where you modify the device a little bit, but okay. So now going back, so if you have a quantum state, and hydrogen atom is an example, but you can take for example, a superconducting circuit. It behaves, the laws governing that are nearly identical to this two-level system of 0 and 1, and then you can superpose them. And superposition is absolutely critical to quantum computation. Without it, there is no quantum computation. And one such state itself is not also useful, meaning if you just build one, you have to have a minimum of two. Just like we talked about the exclusion principle needed two to discover something new. Right? So then comes this idea of entanglement. The moment you have two qubits, two-level systems, now you can sort of imagine there are two hydrogen atoms. Don't think of a molecule. Molecule is basically one system again, because it sort of condenses and then the energy levels get. So this is just one system. But two hydrogen atoms are far apart, let's say. But then there's a photon going between them. So this emits, the other absorbs, the other emits, and this absorbs. So somehow they're attached. And we know that already, thinking of it this way. And so now the states of the system can be the following. So atom 1 can be in state 0 or can be in state 1. Atom 2 can be in state 0 or state 1. So there are 4 possibilities already, right? And so those 4 are called the basis states. But because of the photon going back and forth, you have this 4-dimensional space now where you have a vector. For the one atom, the vector, by the way, for the quantum system, even one atom and 2 mirrors around it and 1 photon, that state of the system is not only the north and south pole of that, we're thinking of some sort of abstract sphere, but it actually, because these two coefficients, or rather it's some constant times state 0 plus some other constant times state 1. Now the governing dynamical laws of quantum mechanics, which is the Schrödinger equation, is different from Newton's laws in the following way. Obviously, it's a wave function and all that, but it's a fundamental mathematical structure. The difference is it has a complex number in it. It's called a complex diffusion equation. The dynamical law is like IH bar d by dt is equal to the energy and all that. A complex diffusion equation allows for something that classical diffusion equation doesn't allow, and that's interference between two paths. And it preserves it. It actually preserves the whole interference of the phases of the matter because it's the complexity. Whereas in classical physics, the phase is washed out from the start. When you have matter, obviously in classical physics, when you have light itself, the phase information is all there, right? But it doesn't have the particle nature that you kind of need to do the computation. So only when you have wave-particle duality, you have both. So this is very important, and this is underlying principle why quantum computation has a chance. Or rather, this is the engine we're going to use to make quantum computers, this physics of it, right? So it's a complex diffusion equation, and that being some more mathematical concept, but in reality, what it really means is that if I look at the dynamical laws of one hydrogen atom with 0 and 1 state, and then a photon, then the states of that object is not just the north and south pole of a picture, but the entire surface of that globe. That vector can point anywhere on that. It's the entire, so in other words, the vector, because both these momentum and energy or whatever you think of it can have real and imaginary parts, so to speak. So you take a tensor product, so to speak, you take x-axis, y-axis, but you rotate all of them and you form the sphere out of that, right? So that's all possible number of states of one qubit. And that's amazing because it can sample all those states based on how you initialize it. And that is sort of an immense change from just 2 points, right? I mean, you have a whole list of points. Now it has some issues that when you measure it, you can't measure all the points, it will go only one place. It's doing all the physics under the hood. But when you try to probe it, it will always go into one of those states. And you have to conclude from there, what was it to, I mean, so you have to, in other words, the challenge we will see soon is the challenge in quantum computation is not so much of how you compute, but how you ask the question. It's very, very important to formulate it right so that you get the right answer in the end. So that's all, the Shor and the Grover algorithm is all about. What's your, how do you formulate it? So maybe I'm speaking by bit far ahead, but now when you have two qubits, because you have the 0, 0, 0, 1, 1, 0, or 1, 1, 4 states, right? The dimensionality of the space becomes 4-dimensional right away. So it's a hypersphere now where instead of a 3D sphere, you have now 4D space. And the complex coefficients of each now sample a whole lot of more space. So the system can sample a lot more states, which it couldn't otherwise, right? If you had digital, it would only have maybe 4, right? I mean, there's 2 to the power 2 here. So now, and that's okay. That's also not that exciting, but entanglement is a very interesting property where you can say, I have this state, yeah, one atom, let's say it's in state 0 or 1, right? The other is also in some superposition 0 or 1. So the combined state is some sort of a product of the two, right? That's a very simple thought. Sure enough, and you can do all the tensor, these are called tensor products of the two states, alpha 1 times 0 plus alpha 2 times 1, beta 1. They are called tensor products, right? But what's quite amazing is there are some states you can write down by hand, which is not a tensor product of the two. That the two things are not behaving individually and you're just sort of gluing them. It's not like that. And these are called entangled states. Entangled states, a great example is the famously called the Bell state, after the Bell identity and all that, which led to the EPR paradox. So this is very simple. It says it's 0, 0 plus 1, 1, or 0, 0 minus 1, 1, meaning both are zeros or both are ones. Now this is an entangled state. It cannot be written as a product of the two states, two wave functions or two states. And here the system is behaving as it is one system now, one quantum system, not two. It has lost its individual identity. I as a very bad example, perhaps, a boy and girl meet, they go back, they are not entangled, right? But if they have a kid, they are entangled, right? So there is a it's very hard to sort of decouple them anymore because of, because something has happened. I mean, maybe that's not a great example, but I'm saying it's somewhat like that. It's very much like that once they're entangled, it's not possible to find their individual identity, so to speak, anymore in this system, in this particular system. But what bothered Einstein about this picture, which is a logical conclusion of quantum mechanics itself, is that if you extend it, then how far can you take it? What if your other hydrogen atom is, in another planet? No problem. You can, they can be entangled, and you can pull them apart. It's okay. There's nothing restricting it. And then if you test something here, you can immediately conclude something about there. Right? What happened in planet, immediately meaning instantaneously, and that seemed to violate speed of light being a cosmic limit of things, which is the foundation behind the EPR paradox. Yeah.
So talk to me about this a little bit, that this whole phenomena of entanglement, it wasn't observed in an experiment initially, right? It was all theory.
That is correct. So, yeah, go ahead. Yeah.
So what's the thought experiment here, that how does one even come up with this idea that two electrons will be entangled in a completely, yeah,
in the scenario. So actually, when people started looking at the many electron systems, as I was mentioning earlier, already it was quite clear that if you look at, say, an element like, say, silicon, which is a great example, it has this many electrons, not one, and the location of any electron is quite tied to location of all others, because they are getting attracted by the nucleus. They're also repelling each other, and they're all waves, and they're all particles, so they're all constrained to all these laws. So essentially, if you do something to one, something happens to the others as well. So this sort of entanglement came already from the idea that even an atom itself, within itself, electrons within itself, there's, I don't want to say that's a great example of entanglement, but that came, the idea that you must have a many particle sort of a function that is capable of handling many particles. But in that system, in a hydrogen atom, for example, or sorry, in a silicon atom, if you write the wave functions, you can disentangle them. It's not an entangled state. What I mean is, I can write the wave function as, for 10 electrons as psi1 times psi2 times psi3 plus psi3, something like that, plus some linear combinations of it. This is called a fermionic state determinant. But an entangled state was sort of created by Einstein and many others at around the same time, who were trying to prove that quantum mechanics is not complete. They were trying to literally find holes in the Schrödinger equation and the quantum theory itself, that a state of a function must be represented by a wave function, and for multiparticle systems, it must be a multiparticle wave function. And what they were trying to create was states where which are consistent with quantum mechanics, but not consistent with some other physical laws such as relativity and speed of light. And this state was really, in a way created by, because quantum mechanics allows for all superpositions, right? So any superposition you write, it should not violate any laws of physics, right? Clearly, it doesn't violate the laws of quantum mechanics, but what Einstein and Podolsky and Rosen, they came up with this idea that if I create a state like this, which is an entangled state, famously, then it seems to be violating the fact that if I measure something here, then so this was famously called the spooky action at a distance. Yeah, go ahead.
Yeah.
Go ahead. Yeah.
So this is the picture I have in mind, and it feels incomplete. Like people say that, like, like you have two electrons, you shine some like laser on something, two electrons separate, but because they came from the same thing, the spin must be opposite. And so hence they are entangled. Now we take these
Correct.
electrons far apart, and then like you measure the spin of one, the spin of the other. How do you take them apart? Like, as in, maybe a very dumb question, but
No, not at all, not at all. By the way, all those processes also change the internal coordinates of the system, meaning when you start to pulling something out, especially separating them, then some other things change. But many of them, experimentalists have figured out ways to move quantum particles spatially apart without changing certain degrees of freedom. For example, the spin is actually quite a robust state of the system, which if you avoid magnetic impurities or if you pull the electron through vacuum, you're not going to be able to change its spin at all. It's going to be preserved. So in a vacuum, you can always put an electron in an electric field and it will sort of move, but it's not going to change one of its coordinates. So I think I'm not trying to say at all that these are easy things to do, but I think there are tools and experimental methods by which you can probe a hydrogen atom here and a hydrogen atom across the town through a laser, through a light beam in an optical fiber through a single photon. Those are all doable today. For example, I think experiments have done across a city teleportation. Basically, this experiment I was talking about, hypothetically, I have two atoms and creating a Bell state out of it, where you have this entangled state with a photon going back and forth. That's sort of very doable today. So those have been used to probe what's called the EPR paradox, right? So when EPR came along, they posed this as a paradox that is seemingly violating certain things, and Einstein, I think, famously for the last 20 years of his career, he tried to. So there's sort of a conflict between what's called local realism, that according to classical laws of physics, all laws that determine the state of a system are local, meaning it is governed by differential equations. So that means if you change something, only local things matter. What's very far from it cannot have a direct influence, instantaneous influence on it. And Einstein tried to kind of prove that, and he thought that the EPR paradox is unsolvable, meaning it shows that quantum mechanics is not complete, so to speak. It's not accurate. Yeah. But then I think Einstein didn't live long enough for John Bell to have come up with his. So what John Bell did was he said that, okay, so here's an experiment. This is a famous experiment that John Bell introduced, that the 0, 0, and 1, 1, sort of the entangled state. Entangled state is the famous Schrödinger cat state, whether it's dead or alive, we don't know from outside the box. Sort of like that, basically. But what John Bell came up with is, here's an experiment, do this. If the probability that you get in the end of the measurement is below a certain number, let's say it's 0.75, then Einstein was right. And if it is like 0.85, which he predicted would be correct, if then quantum mechanics is right and Einstein was wrong about the local realism. That happened in the late 60s, unfortunately, not long enough for Einstein to have seen it. And if he knew that experiment, he wouldn't have wasted 20 years of his life. Because immediately after that, Bell's prediction, people did a lot of experiments. They continue doing it today. Every year you'll find a couple of papers, verification of Bell's identities. And indeed, it's always been 0.85, meaning that the local realism aspects of it is not quite true. Entangled states are real. And then it's actually, what's quite interesting is, and this is a little bit philosophical question too, but it does not really violate anything in many ways, because information is not sort of transmitted either. But nevertheless, yeah, so the Bell theorem proved that entangled states are real, and it's you can entangle things over large distances, macroscopic distances, which is kind of absolutely amazing. That sort of the quantum systems are thought to be very delicate. You do something and it changes, but over 50, 100 miles, people have been able to entangle now states that are essentially entangled. And then this entanglement is the power, sort of that's the energy that powers the quantum computation. Even with single qubits, you can't do quantum computation till you have this entanglement property. That's what brings the massive scaling and massive power. So, yeah. Anyway, so that property came around, Bell around 60s and 70s, so it's relatively new in that sense. So, but not that new anymore. I mean, now it's been almost 50 years since, something like that. And so now, after the Bell, many people in the US and some other countries obviously as well, they said that, okay, now we should seriously think about making quantum computers using entanglement. And famously Feynman and many people who really said that we have already done amazing things with Newton's laws of classical physics. We have landed stuff on the moon and Mars and all. I mean, now in Mars, and sent out gravitational probes outside the solar system. But now here's laws that we understand, which are new. We should be able to build new machines, new engines based on them. And that's really the power in the computation. Yeah, right.
So
sorry, it's become too much of a monologue. Yeah, go ahead. Yeah.
Who makes this connection for the first time, that because of entanglement, we could have more powerful computers?
Yeah, so it's a very good question too. So I would say that people such as around the time of Feynman, which was early 80s, already maybe late 70s, already had a notion that this can make better computers, but they didn't sort of offer a solid. They sort of were more like they were cheerleading. Like, think of something new. Think of how. And the reason for that was around the same time, most of the classical algorithms were also being developed, right? I mean, all the digital classical computation was many of the algorithms for computation were being developed, right? So the way it started was people were not trying to think initially of a quantum computer immediately, but saying that, well, here's a classical task, right? If I bring in a little slice of this quantum, entanglement and all, can I do something better, and all that? So that was initially the thought process. And I don't know about who specifically, but I can say the ones I am quite aware of. I would say, for example, Asher Perez, who was a physicist in Technion in Israel. He came up with a sort of a communication protocol where if you use a little bit of quantum spins and entanglement, then you can for example, I forget the exact mathematical problem that he was trying to do, but it was related to error correction in classical computation. When you have unintended bit flips and all that, then how do you recover your original computation when you have. So using some aspects of entanglement. He showed in early 80s, if I'm not wrong, that you can actually do something like this. And then around, but around perhaps I would say late 80s, early 90s is when it moved into high gear, where a lot of classical computation trained algorithm and CS people as well, they got into this, and Charlie Bennett and others at IBM got into this, and they started saying that, okay, so what are the most difficult tasks in classical computation, right? So search or prime factorization and all those things. How do you can this potential availability of entanglement power quantum computation help in either speeding up something or doing a better energy efficient search or something like that. So that started around late 80s, and I can maybe recount a couple that I know concretely about. I think so David Deutsch in UK had a well-known idea, but maybe one of the most interesting ones was I feel in 1984 there's a very famous protocol called the BB84. BB for Charlie Bennett and Prasad, the two physicists, discovered in 1984. So it's called the BB84 protocol. This is a protocol of quantum key distribution. Basically, it's about communications, not computation, or secure communication. I want to communicate something with you. How can I do that with no eavesdropper, being able to read it? And if an eavesdropper had read it, then I know, I would know, the reader would know, and the sender would know, right? So you don't do whatever you had decided or whatever, right? And so they used the entanglement and the EPR, all the sort of Bell state ideas, to do a quantum key distribution and come up with this algorithm for the first QKD or quantum distribution. So it's the beginning of a practical implementation. They use the polarization of a photon and a photon quantum properties of photons, and they actually experimentally demonstrated it. So they actually showed that this is actually doable, right? So that was a very big change. I feel the BB84 is the first algorithm, not for computation, but for communications. It's encryption and cryptography. It has great importance in that. And that led to now many quantum communication algorithms and protocols that have been used in quite dramatically interesting ways. Now, communications is the first place where quantum is real. I mean, quantum algorithms are being used today. It's not like it's a future, it's happening now. And that's. Then there were a string of other problems, and the ones I know of is not too far from where you are in Berkeley. There was the famous Bernstein-Vazirani theorem algorithm, where they showed that there's a bit of a, maybe I would say, a very interesting mathematical problem, but it's a contrived problem, which classically it's very hard to solve. But they showed that if you use a quantum computer for that, you can do something in one shot, which would require some n square, tries in a classical computer, something like. I'm not maybe getting the numbers right here. And then after that there were a couple of very practical problems. There was a famous one by Simon, which is about finding period finding of sequences of numbers. And Vazirani's and Bernstein's theorem was what motivated Peter Shor to start looking for a more practical problem rather than somewhat of a contrived problem, which is made to look the quantum computer good. Right? So, and what Peter Shor was amazingly and absolutely a stroke of genius, so to speak. What he was able to do was, I know we're maybe talking a bit on abstract here, but what he really showed was if you take some of the, he showed that prime factorization can be mapped, as I think very well known for mathematicians, to this modular arithmetic problem where you find the remainders. I think, Kanpur also had some great contribution to this idea is now prime factorization problem. And factorization problem is so critical for, RSA and all these other things, right? So what he showed was if you, once you map it to the modular arithmetic problem then it reduces to a problem of finding the period of a sequence of numbers. period of a sequence of numbers. And that was sort of kind of gotten by Simon before him. How do you use a quantum computer to make a good detector of periods? And he merged the two to find an algorithm which uses a quantum computer to, as you know very well, the classical FFT reduced the computational complexity from, what was it, like n squared to n log n, right? Which was a great development. And now that reduces, this algorithm reduces with the quantum to, I think, what is it, log n now, or cube root of log n or something like that. It's even bigger change, right, so to speak, in terms of the computational complexity, but if you had the quantum computer. So that's Shor's algorithm. The main crux of the matter is, if you have gates that are first, every quantum gate is reversible. It has to be reversible. There are classical gates like that too, like C-dot gate and all. And the quantum gates are sort of very similar in spirit, but what it has, which the classical gate doesn't have, is it has this sort of, it preserves the phase all throughout the computation. With the classical gate, every time it does a measurement, it loses the phase, but it retains the amplitude, so to speak. So one cannot, I mean, for example, in our labs, we do period finding all the time. We make a crystal. What's a crystal? It's a periodic arrangement of atoms in space. How do we find period? We take that crystal, shine an X-ray beam on it. It's a waves, right? And when the waves match up with or we rotate the crystal, and at a certain direction, we see a very huge peak. That's X-ray. We measure the periodicity of atoms in a physical location of a crystal. And that has nothing to do with quantum mechanics at all. You shine a wave through a grating, you can find the period easily, right? No problem, right? It's a classical physics problem. All of us use it, and knowingly or unknowingly. But the quantum period finding is a different matter here, I feel, because you are finding the period of a sequence of numbers. And of course, the Fourier transform is, so the actual Shor algorithm is slight variation of the DFT, discrete Fourier transform. It is called the quantum Fourier transform, where all the elements are sort of complex numbers now, cube roots of unity and all that. And it uses it in a very clever way, as long as you can build these gates out of the entangled qubits. You know? Anyway, those are a very mismatched picture maybe now, but anyway, that's sort of the basic idea I feel there. Yeah.
Okay.
And after Shor, I mean, sorry, go ahead.
No, why don't you finish your thought?
Yeah, I just want to say one more thing that, but Shor didn't sort of stop there, because immediately after Shor's algorithm came also the Grover algorithm for search, you know, it reducing the depth of a search, I mean, or the complexity of the search as well. But the big concern that was posed immediately by people like Rolf Landauer and many people who knew the limitations is, this is absolutely fascinating, Shor algorithm, Grover algorithm. These are practical things, right? Not necessarily a contrived problem, so to speak. I mean, contrived problems have their importance because they led to this, right? But it's practical. But actually, to realize it, you need to have error correction. And without error correction, you can't, I mean, you can't really compute, because if you, I think that's sort of a very well-known thing, that if you can't correct for errors, there's no way of finishing a computation of a reasonable size or any of something that would actually matter for something, right? And this is a severe problem in quantum computation, way more than in classical computation, because in classical computation, you get a 0 or 1. If you are 0.9, you know it's a 1. If it's 0.1, you know it's a 0. But in quantum computation, if you're slightly away from, because remember, your whole space is a computational space. If you're slightly away in a different quantum state, and it has much more prone to error, way more prone to error. And on top of that, there's a big problem that in quantum systems, in classical systems, how do you correct errors? Well, you find something that you are deviated slightly, then you sort of you need to copy, you need to produce the same state again, right? You need to do that stimulated emission, clone it, right? But in quantum, there's a theorem called the no cloning theorem. The moment you measure a state to know what state it is in, it goes into one or the other. So that sort of seemingly completely forbids the possibility of error correction, seemingly.
mm,
But around 85 or 86 is when Landauer and all posed this problem that you can't do error correction, so it's futile to make quantum computers. And then many groups, and Peter Shor being one of the earliest, showed, using some ideas from Asher Perez and all, that actually quite amazingly, if you entangle in a certain way, if you need to do a 2-qubit operation, but if you use 8 qubits, maybe, and you use a certain particular kind of linear combination, then you can correct errors. So it's possible. So they proved it around 99, 2000, and all actual quantum computers have been built right after that, where this was proven by Shor and a few others who kind of
mm,
showed that you can actually correct errors, which is, to me, even more dramatic than you can actually compute,
mm,
because
mm.
practically it's okay, you can compute by many ways, but most of them fall short because you can't correct the errors. But the error correction was actually very, very good. Anyway, so
So,
I know we are going a bit over, but yeah, go ahead. Yeah,
so this is the idea that like you may have 1,000 physical qubits, but for
that's right.
computation, you may have effectively maybe 100 or
That's
so
right.
qubits
That is
that you
correct.
can really rely on because the error correction has been built into it. Right?
That is correct. And even digital computation is done that way today. I mean, all the
Yeah,
Reed-Solomon
yeah,
codes, all the coding, and they all have the
yeah,
one or two ways of doing it, right? So yeah, right, right.
yeah. The memory has error correction, communication has
That's right.
error correction. Uh, so now talk to me about the physics of quantum computer. Like when people are saying they've built like 500 qubit, 1,000 qubit computers, what are they building? What is like physically there, and what are the challenges and like where the frontier lies?
Yeah. So now we're getting into something we do every day. So I'm going to be hopefully, be able to share with you what where things are and all that in the
Mm,
today. So really, currently there are around that time, turn of the century. Literally, this is really a 21st century device, the quantum computer.
mm,
So today there are 3 parallel paths. Maybe I should 4 parallel paths trying to build the quantum computer,
mm,
and there may be more in the future. I mean, we are honestly very early in this game.
mm,
Even today, I think, in spite of the history we discussed. So the most advanced version right now is based on superconductors. So whenever you hear that IBM or Google released this Sycamore processor with 100 qubits, or 50 qubits or 400 qubits,
mm,
those are all based on superconducting circuits. So,
mm,
and that's one of the ones I'm also personally working on now,
mm,
with a few other colleagues and universities and all that. And I'll just mention the others, and then I can describe to you a little bit in more detail about this particular one, right? So
mm,
there are 3 other variants. One is called trapped ions.
mm,
In that process, and I have a colleague here and a few other groups in the world, what they do is they take literally an ion that is trapped due to some electromagnetic, electric fields on a CMOS chip, on a silicon chip. You trap
mm,
the ion and just hold it there. And then you have a laser beam that comes in and hits it and then goes and talks to another ion. It's literally, you're making EPR, Bell states, or
mm,
entanglement with atomic systems on a chip.
mm,
The problem with the atom being inside the solid is it's prone to a lot of decoherence mechanisms. It's
mm,
vibrating, it's getting stuck by some electrons or something like that every now and a while. But if you are outside, it's immune to some temperature and decoherence. Right?
mm,
So it has to maintain its quantum nature, but if you put it in a crystal, you are subject to becoming more and more classical now with
mm,
equipartition and all that. So you
mm,
need to kind of move it out of that. So that's called trapped ion. There are many companies, IonQ and many others, that are doing great work on the quantinuum. They are scaling also. The
mm,
systems are generally could be a little large because they need lasers and all that sort of thing outside. But it has the potential of being done at room temperature. There are obviously challenges in many things, like when you are having the laser beam go across. It's kind of amazing if you think about it, that all these things have, the laser was also built with all these ideas and the atoms, but
mm,
now we are using it in some clever way that nature hasn't done yet. So that's kind of the
mm,
interesting part here. So that's trapped ions. Then there is spin qubits. Spin qubits are basically very similar to transistors that we already make. Here, what we do is to mimic the atom, a two-level system, which we need for the qubit, two energy levels, we make a semiconductor very, very small, and it becomes a quantum dot. It has energy eigenvalues, energies of electrons that are quantized and separated now, and we zone into two of them and try to use them as the qubit, as superpose them and entangle them. This has the highest chance of scaling to very large number of qubits, but it has also tremendous challenges because it's a sort of a solid state object. It's also prone to a lot of decoherence and classical processes, but progress is being made. I mean, Intel and many other companies have projects, HRL and all, are doing work in this area. Then there is another one that has come up in the last 3 or 4 years from Harvard and related places called the Rydberg atoms. It's very similar in some sense to the trapped ion, but not exactly. It's similar. Also has a lot of promise. And but actually, most of the real computations still today, as far as I know, examples of some algorithms run. You can run one remotely as a data server from IBM today. I think your previous Dr. Zori, she also mentioned she was working in that area, right, where you can have a web service offered where you can actually write code and do manipulations on quantum computer. Those are all based on superconducting qubits. So the superconducting qubit is a very interesting device in many ways. First of all, if you are doing making a qubit, for example, with a light and an atom, you have only one photon. So you have one light. If you have many, you are back to classical. You're not doing qubits. So you're at the level of one photon. So you must not lose that one, because then it's over, right? There's nothing else to do. So you need superconducting qubits operate in a microwave frequency range, which is, say 5 gigahertz, 5 to 10 gigahertz today. So you have one photon, which is a microwave photon. It has that frequency, and you can calculate its energy accordingly. It will be, maybe a milli-electron volt or something like that. And where that photon needs to be going back and forth between mirrors, and there has to be an atom in between, which causes two states, and it will sort of get absorbed or superpose it. So those lines have to be lossless for microwave electrical signals, and the only thing we know today is a superconductor. Superconductor has zero loss, when the electrical current flows in it. Then we need an atom-like thing in between where the photon sort of excites that and causes these transitions and all that. And that thing today, what is used is called a Josephson junction. A Josephson junction is two superconductors separated by an extremely thin, about 1 nanometer insulating layer. So what happens is, this is an absolutely magical, fascinating device. It was discovered in 1963 after superconductors were discovered. So in this device, there can be a current that will flow across these two electrodes through the insulator. It will tunnel through, quantum mechanically tunnel through with no loss. So you can imagine there are two superconductors, both of them are lossless, but you have put an insulator in between them. Right? It should be very high resistance, but actually it tunnels through without any resistance. And so these electrons form some sort of, it's actually a correlated fluid, superfluid. So and then if you have a microwave, it sort of oscillates through it, goes back and forth. And those energy states, if you write out the equations, they form what's called the harmonic oscillator energy relation. And harmonic oscillator has a precisely quantized energy levels. It only allows this or that, and nothing in between. It's like a quantized level. And this particular Josephson junction, if you had a perfect harmonic oscillator, then your first state, second state, third state, the spacings are all the same. This is a very classical property of, quantum property, but it's a well-known property of a harmonic oscillator, that the spacings of energy become exactly equal. That's not true for a hydrogen atom. It goes 1 over n squared. So the first spacing is large, then it gets smaller, smaller. So the problem with all spacings being equal is that if a photon can excite from state 0 to 1, it can also excite from 1 to 2. But that is a dimension of the space you don't want to go there. Your whole qubit should be made of only 2 states.
mm,
So luckily, what happens is Josephson junction, quite amazingly actually, is a slightly nonlinear harmonic oscillator. It's not a linear
mm,
harmonic oscillator. So the
mm,
spacings are not exactly the same. So it's slightly different.
mm,
And so this is the core qubit. Qubit is the following. I'm saying it is simple, and it is actually simple. It's not complicated. It's two long metallic superconducting line strips of a certain
mm,
wavelength, and that
mm,
wavelength is exactly half wavelength of the photon wavelength. You
mm,
do speed of light and frequency of the microwave frequency. And in between, there is what is our artificial atom. That's just a Josephson junction. Two superconductors could be the same superconductor as you build a line with a very tiny insulator in between.
mm,
And the way you do the quantum computation with it, the qubit, is you have a microwave line, a microwave connection that excites, that radiates this thing with a microwave pulse.
mm, mm,
And then the qubit will start sampling the entire sphere space. If you let it go,
mm,
it follows the laws of quantum physics. It undergoes what are called Rabi oscillations. These
mm,
are, if you start out from one, it will oscillate, go back
mm,
south pole, come back. It'll keep doing that. If we
mm,
could build a qubit like this that could keep its oscillations for say hours,
mm,
tomorrow we will have the most powerful quantum computer.
mm,
Because today the big problem is this works as a qubit, perfectly as a qubit. Everything that has been promised about a qubit, it does it. But it only does it, today's record is 1 millisecond. It only is coherent for 1
yeah.
millisecond, and beyond that, it decays, becomes more classical. You lose the coherence
Mm,
of the quantum system.
mm,
This is a problem with the superconducting qubits. But
mm,
because it is so similar to classical circuits, all computation is done with currents and voltages.
mm,
You don't need lasers. You don't need any other stuff. It's just done in a very
mm,
similar way. So that's why
mm,
it's very practical to build circuits with it.
mm,
And that's why the Google effort, IBM effort. So this particular thing is called a transmon. It's a transmission line with a ON at the end for,
mm,
like electron, photons. It's a transmon.
mm,
It's called a
mm,
transmon qubit. And this was initially really developed and discovered at Yale University
mm,
and by Michel Devoret and Richard, Bob Sholkoff and others. And then on the West Coast also by uh, John Martinez, whose company, who basically Google literally bought their lab to do their quantum computation effort from Santa Barbara. So this has progressed, but I think what we are hitting this wall of coherence. And some
mm,
of the work I do and with some colleagues from Yale and other places is, can we find, this combination of materials to take this coherence from milliseconds to much higher values so that we can open up the possibility of practical quantum computation.
mm,
Millisecond is already allowing for a 100 qubit system to be realized, but I
mm.
think it's not enough yet to do big problems yet. Now, the
So,
other three approaches could be also rising fast. I mean, I'm not saying
mm.
that they're behind, but some of them can also do that. But okay, yeah, go ahead.
So the question was, how, what is the relationship between the duration for which the qubit is stable and number of qubits?
Great, yeah. So very good question, and this is very much deeply tied to the what can you do with if you had a million qubits which all have millisecond, can you do much better than?
Mm,
So yeah, so actually the problem with this is sort of also related to the speed of light restriction. Is
mm,
light travels a foot per nanosecond, even though we say it's very fast, but actually if you know about what happens in classical communication systems, the speed of light is limits. You
mm,
literally can make billions of dollars by cutting down the delay time of light transmission by a microsecond, for example, right, for
mm,
stock trading and all that. So for entangled system, for example, a qubit here has to transmit and connect through via light. A microwave is a photon
mm,
is a light signal too, so it has to communicate. And so if it is entangled with another state, and if the state gets farther and farther apart, then a millisecond is not enough for it to wait. I mean, it has to wait for the photon to literally bounce back.
mm,
But if you restrict the time, it is dead by the time sort of
mm,
the photon comes back. So you lose entanglement completely. So improving both is important. Improving the density at which we can build them, close pack them, very close to each other so that the light doesn't have to go far, and also increasing the coherence of each qubit are equally important right now. And error corrections are being developed for one way or the other, or both, taking sort of meeting halfway for both. But it is very important, even if we can make a billion qubits, spatially, they will be separated. And the light, or sort of this entanglement, costs time. And that time is very premium in making sure that you have a successful quantum computation. I don't know whether I'm answering correctly, but I think that's the idea that if you're doing computation in this way, you need to actually be coherent at least till the time of one light path. So
And so physically, these things are probably on a semiconductor wafer in a 2D grid.
Currently, the microwave, the transform qubit, superconducting qubit, indeed, these are built on either silicon or sapphire-like wafers using completely silicon-like processes. And it's a 2D surface, but now increasingly there's also wafer bonding, so you can stack them and connect vertically too. For example, transmission lines can be on one side, and so there are various geometries being considered, but essentially all of them are using the standard, sort of a silicon semiconductor process for now for the superconducting qubit, but also the spin qubit I mentioned, where we have quantum dots. Those two are using semiconductor processes. Even the trapped ion is using semiconductor process to trap the ions and then bringing in optical fibers to only the Rydberg states, which is a relatively new one, doesn't use semiconductors. They use literally what they do is they have a laser beams and they trap atoms in excited states at the points of intersection of the laser beams. And then they can literally move the atoms close to each other to entangle them and take them apart. Whereas the superconductor qubit I mentioned is where the qubits are physically located, fixed in space. It's the photons that are doing the talking. Here in the more modern version Rydberg, that's a non-semiconductor process-based one. Quite exciting, I think. But I'm following it, but I don't work on it yet myself.
So since you brought superconductors, the thing that one reads in news is that the biggest problem with superconductors is temperature, right? That you have to cool down quite a bit for them to work. And the other thing is, what are the challenges around packing them close by? Because it seems like that is a big deal in terms of getting more qubits. Is it like similar to the shrinkage of the feature size and classical microprocessor building, that like how fine of a feature can you build on semiconductors so that you can have smaller and smaller gates?
So both are very important questions. So let me start with the temperature part, and then we talk about the integration and packing part of it. So temperature actually used to be a problem, but now, first of all, it is a problem because we don't have a room temperature superconductor till today, right? So not that it won't happen. I think it will happen, but it hasn't happened yet. So, and when it'll happen, it'll be a great day. So it's a separate matter.
We don't need quantum computers in our cell phone and laptops, right?
That is true.
As long as it's
as you know,
sitting in a
data center. So, and the systems that are used today, all you need to do is, if your dephasing process has some characteristic temperature T, and superconducting transition temperature, the ones we use typically are currently use an niobium or these things, which are or even aluminum. So they are about a Kelvin or so of 10 Kelvin sort of temperature below which they become superconducting. But we need to be quite below that too. So currently, these things called dilution refrigerators, DILFridge, these are built to go to 10 millikelvin, 0.01 Kelvin. And these are standard, and all the data, all the stuff you see from IBM, Google, they all use DILFridges. I mean, these vertical things with multiple. So we have one in our lab, a few here. So they go to 10 millikelvin, and once you put it there, it is literally quite stable. And I want to say that the temperature problem, it's there, but you pay some energy cost for cooling, and
mm,
it's okay. After that, you can build a circuit, it will sit at 10 millikelvin forever. It's okay. It's not a huge problem now.
mm,
I would say that obviously, so the company that builds some of these pulse tubes and all are in Syracuse, and then the big company that integrates them is in Finland called Blue Force, and there are a few others. But I mean, they're building good equipment, and those are
mm,
generally quite good to be able to meet the temperature requirement. It's
mm,
not a showstopper.
mm,
The second one is a bigger problem in the sense
mm,
that when you pack it, what's being observed is if you make a qubit, the transform qubit bigger, it has better
mm,
coherence.
mm,
But that's unfortunately not very good for integration, So because you have to connect many the size. If you want to make 10,000, then suddenly you need a space which is that big. All of that has to be at 10 millikelvin. So it's really related to packing problem. And not only
mm,
that, you need a lot of controls. You need a lot of, to read or write to initialize a qubit in a particular state, in a particular superposition, put a gate on it, Hadamard gate or,
mm,
C0 gate on it. You need
mm,
to have microwave lines, microwave photons going at a certain pulse and all that. So
mm,
this is a much more severe challenge, in the sense, how
mm,
do you form the interconnects
mm,
which
mm,
get in the signal and get out the signal from the
mm,
quantum computer. Even the
mm,
quantum computer itself may not be very difficult in the long run, but the whole read write of it is a big
mm,
challenge, I feel, very big challenge. And there are a lot of efforts, federally supported efforts, as well as companies that are trying to address this
mm,
matter. I mean, not unknown to people who have gone through this for digital computers. I mean,
mm,
interconnect is the most energy consuming thing in current microprocessors, today's microprocessors.
mm,
No more,
mm,
not the transistor anymore. It's really, people have made power vias and changed the way you power up
mm,
the billion billion transistor circuits today, microprocessors today, because interconnect it's very hard to, even in digital world, it's very hard to connect a billion transistors on a 2D
mm,
surface, right? So spatially and time delays and all. So in the quantum computer, that is a bigger challenge, I feel. But many interesting people are quite clever and
mm.
they're making good progress in that as well. Yeah,
So
yeah.
let's project into future. What do you see sort of the trajectory? I mean, it's always nonlinear when it comes to innovation, but uh,
Yeah. So I'm personally, very optimistic about
mm,
quantum computation. I have, there are a lot of naysayers, obviously, all the time, but I feel looking back historically, technologies move generally much faster than people think it will.
mm,
Generally, it has been true. And as far as quantum computation goes, uh, the fact that we have already quantum computers is saying something very big, that it's here to stay. And there may be, we will hit walls. I mean, for example, I told you about transmons. We are hitting this 1 millisecond time wall now.
mm,
But the first transmon was made around 2003 or 4.
mm,
Actually, the previous version of it was called the Cooper pair box by Nakamura and all, which showed Rabi oscillations for the first time in this system, the quantum coherence. That was built around 2000, and the lifetime of that was 1 nanosecond.
mm,
So now it's a millisecond, and
mm,
it gets harder, obviously, as we move forward. But it's it is a problem where we know what to do. It's
mm,
not like there's no direction. And once that
mm,
happens, I think the efforts are quite focused, and then when they get focused, then we find solutions faster. So there's a lot of beautiful engineering to be done here, but I feel, I mean, I'm saying that, for example, one of the things we are trying to do here is trying to identify what is the cause of the decoherence. It's not necessarily clear which particular mode are we losing that photon into. It's not clear. So it's sort of a great puzzle and mystery, but it requires a lot of material science and measurements and metrology. Anyway, I'm very optimistic it's going to work out. I think David Mermin here, who a very famous statement is a very, it would be very rash to say that only a rash person would say that we won't have a usable practical quantum computer by 1950. But only a very rash person will say that we will not have one either. So because the part of technology is it moves faster than we think it is. Generally, I felt that way.
Yeah.
I've seen
Yeah.
that in my grad school effort. We were working on these gallium nitride transistors at that time. We didn't think it's going to go anywhere. I mean, we're like, oh, it's a curiosity. Gallium nitride LEDs and lasers, we knew it's going. We had very clear
Mm,
idea where it will be, and it has been there. But
mm,
nitride transistors have become bigger than LEDs now because they are in all our, chargers, cell phones, and all that, and it's entering. So that was a big surprise. We thought, well, it's
mm,
possible, but nobody's going to ever do it. Similarly, if you look back in semiconductor technology, the founders of this technology, Shockley, Boddy,
mm,
they had no idea that semiconductor transistors would be used for computation. They were developing it for power amplification for Bell
mm,
Labs for communication systems. I mean, and it happened way faster than what they had even imagined, or they hadn't
mm,
imagined it would happen there. So
mm,
I'm quite optimistic about quantum computation. The challenge for me is the following: that I think what is needed is not. I mean, engineers and all will work on it, and country has to country people have to invest in it. But a challenge would be to find a bigger set of problems other than, say, prime factorization.
mm,
And so there's only a very limited set of problems which have been identified for this sort of harnessing the power
mm.
of quantum computers. That has to be expanded. I think it's sort of a community task, so to speak. People
Yeah.
have to bring the problems and then nice ways to map it to quantum
Mm,
computers. And so it has to be community. And then in the parallel, of course, the physical quantum computers are being developed and
mm,
people are at it. So I think it will happen. But I think it will happen both ways because only certain problems have been thought of for the quantum computer to be useful. But I'm pretty sure there's so much more, just like transistors are doing way more than just communications today, right? So in the
mm,
same way, I think quantum computers sensing and modeling of phenomena and predictive, weather
mm,
patterns, all that stuff. I think that needs to be done. Anyway, so I'm very optimistic about the future. There is a
mm.
technological aspect to it, a material science, device aspect to it, but there's equally a CS aspect of it from algorithm side and trying to identify a larger, richer set of problems which can benefit from a good quantum computer, perhaps. So, yeah.
Very cool. We've been going for almost 2.5 hours.
Oh, I just realized, wow, it seems we are getting started, but I think it's a good place to think about, yeah, wrapping up. But
It's been
yeah, yeah.
so much fun learning from you. I do have one last question um, that maybe a little bit philosophical. So every time I try to understand and grapple with this um, quantum physics, quantum computing, intuitions fail, okay? And what I'm realizing is that we kind of take intuition to be for granted because everything else that we study can be can have an analog in sort of real world,
Real world, yeah.
the observable classical world that we can kind of map to and visualize and think. But
Mhm.
the realization I'm coming to is that maybe some of this stuff that you have to deal with in quantum mechanics and quantum computing, the math behind it has no analogy in the common sense, the classically observable world that our common sense is built on. So
Mhm.
the the idea that somehow we can understand this without really going deep into matrices and um, the math of it just is probably just not possible. At least that's how I'm thinking about it. I'd love your thoughts and opinion on it before we close it.
Yeah, yeah. This is a very good uh, also topic to end the discussion because it's going to go into that philosophical realm. I'll start by saying one thing which I think you may have asked earlier also, that I think the closest classical intuition is the one that I think often people use, which is, and Feynman famously introduced about the double-slit experiment. It,
Mhm.
I think, is the closest one can get to not necessarily how a quantum computer works or how Schur algorithm does, but for the most part, it can come very close to it with thinking of, if you're shooting electrons through slits, then how come that if I shoot only one electron, it goes and hits someplace, but if I shoot a million, then suddenly the histogram looks like it's waves, right? Whereas a single particle is just one particle. It's not like a wave, right? So whereas if I shoot a light beam through double slit, every time I see there's a wave, but if I were to tune down to one photon, again I'll get a particle just as if it hits one point. And the fact that things, be it matter or light, can amplify or destroy, constructively or destructively interfere, is really the basis of all this. So I think the only intuitive thing I have found which connects these is this double slit experiment, and deeper thought of that and all its sort of manifestations one way or the other. Even the Shor algorithm can be thought of that you're feeding, n beams to n slit problem and then using that for the factorization using. But then you're right that we are we generate as human beings, we don't encounter don't feel phenomena that is a hybrid of the two, or matter, particle and light and wave. We either feel one or the other, because on a classical scale, on a large scale, the other part is deeply suppressed. The other nature of it is deeply suppressed, mainly because of this correspondence principle. If you go to very large numbers, you have this delta n, delta phi number, or the phase of number of particles, and the phase of that wave must be greater than or equal to something. So generally, the only things we can feel or touch or sense or smell or see are where one of them is completely suppressed and the other one is very high, because our sensory inputs and all are not sharp enough, not sensitive enough to detect at the single level of the other. By the way, that being said, this is very interesting. Bob Bialek from Princeton gave a talk recently showing that the human eye can see up to a single photon if you do things right. So that's quite interesting. I was quite amazed at that. And anyway, so that being said, I would say that certain things, such as a superconductor, it's really a macroscopic object where the quantum part of it is manifested in a kilometer long wire. The whole thing is one quantum object. So there are very rare things like that where the quantumness is preserved with billions and 10 to the power 20 particles, and that's the whole thing is still coherent, which is why it's being used for the transmon qubit. But I agree that this aspect of very famously, this is called the Copenhagen interpretation of quantum mechanics, that nature is an engine that is going to do all the work, but just don't try to ask about every little detail of how it's doing it. You can only get, if there are a million windows, you can only get to peek from one window, not all of them at the same time, because if you try to peek through that, it becomes classical. So it's somehow doing a lot of work, but if we are clever, we can take advantage of that quantum dynamics. If we, on the other hand, we have always used a classical, I think this is an interesting point of view, that it's more anthropomorphic, meaning human beings have developed from both quantum and classical in many ways. Our birth and our origins are all tied up with that. But our senses have not necessarily, for good reason, I think. Our whole consciousness and existence depends on maybe certainty rather than uncertainty. And maybe we have developed so that we have, somehow nature has realized that if you had that intuition, you won't be an animate object, you won't have consciousness or something like that. So anyway, I think that consciousness may be related to how quantum you are. So maybe, so the most, what we think, which is no consciousness or self-awareness, are atoms, which apparently don't know anything. But who are we to say? So whereas if you have a collection of a very large number of atoms like you and me, somehow we have developed consciousness and become classical. So yeah. Anyway, so that's that.
All right,
I don't know
very
whether I
cool.
answered your question, but anyway, so that's.
Uh,
I don't know whether I answered it.
I think this question also has a quantum nature.
It is true. It is true. Yeah, yeah, yeah. I mean, the Copenhagen argument is, interpretation is, I think famously, I think maybe you have heard it many times, but
Mm,
it is doing it. So just shut up and make use of it. Shut up and calculate is the famous statement for quantum that don't try to be too
mm,
philosophical about it because it's there, whether you believe it or not.
mm.
Use it. Is what that's the famous statement that people use sometimes. But I think we should be philosophical. Why not? It's so rich,
Yeah.
and we should think about its both the beauty and its mysteriousness. That's always good. Yeah.
Maybe let's end this podcast with Schrodinger's cat thought experiment, because
Hmm.
I've heard about it, but I don't think I fully understand it. Like, can
Yeah.
you really do that experiment? Like, why is it just a thought experiment?
Um, yeah. So
So
the
before we go
experiment.
to
Yeah.
maybe just describe the thought experiment.
Yeah. The thought experiment is there's a box and there's a cat inside it, and there is a wheel with poison in it, poison gas. And then there is maybe some sort of a quantum process and a hydrogen atom sitting in its excited state, and it can emit a photon anytime, and that photon goes and hits some detector, and that triggers the wheel to drop, gas to release, and the cat can be dead, right? So,
Mm,
and if that doesn't happen, then the cat is alive. Right?
mm,
So at any given time outside the box, I don't know whether the cat is dead or alive.
mm,
So what is the state of the box? The state of the box is 0, 0, which is the cat is dead, or 1, 1, which is 1, which is the state. So 0, cat is dead, or 1, cat is alive. But it's a superposition. I don't know what it is, right?
mm,
So it can't be 0, or it can't be 1, right?
mm,
So that's the Schrodinger's cat, and it's dependent on a quantum process, the moment I open the box and I see it,
mm,
uh, then it is either alive or dead. So I don't
mm,
know what was the fraction of what was, whether the cat was, at the moment I opened it before. Obviously, if it is alive, then it was alive, right? This is a made up scenario, but if it is dead, you don't know when did it die either, right? So there's
mm,
that uncertainty to that, right?
mm,
Now, quantum Bell state is exactly that. It's really so you can create a cat state where you have this linear superposition of zeros and ones, and even the Hadamard transform on a
mm,
qubit puts it in the cat state, or rather, some of the transforms put them in the cat state, and people do that regularly. In fact, a cat can be one of 16 states at the same point of time, and these are called cat states. But experimentally, obviously, a cat is a classical system, but it's
mhm,
very cleverly tied to a quantum process through this poison and one atom emitting a photon through a
mm,
completely quantum process now, right?
mm, mm,
So it ties the classical to a quantum in a way that we all have emotions about. Oh my God, it's dead now. That's sad.
mm,
Or we can see the outcome quite clearly. So it is also a very important thing. It's also at the base of what can you measure and what can't you measure. So this is
mm,
John Bell's famous book is called The Speakable and Unspeakable in Quantum Mechanics. Basically, we can say we can say about things, but we can't measure about what it's actually doing. So what we say is irrelevant, so to speak.
mm,
But when we measure it, the system changes. So we don't know what was its history at all. So there's no way to know
mm.
it. Anyway, this is interesting and deeper thing one can discuss in longer over maybe some good beers or whiskeys. So yeah,
All right, with that,
yeah.
thank you so much for such an interesting and such a fun discussion.
Thank
And
you
we'll close
again,
it.
Amit, for yeah. Let's close it. But it was really fun, and hopefully, we get to talk about this some other time again. But yeah, I'm also looking forward to hearing of some other people who you might bring on, like Dr. Jody before me
Mm.
in this area. I'd love to hear their It's also a new field. I'd love to hear what other people are thinking beyond the papers and all we read, what sort of more deeper thoughts of them. Thanks for giving me the opportunity also. Yeah.
Yeah, very cool. All right.
All right.
It's good.
Great. Bye.
Okay.